You know, when you look at a modern video game, it's hard not to be blown away. They're just visual masterpieces. And for those of us who actually design and develop these worlds, understanding what's going on under the hood, that's absolutely crucial. So today, we're going to pull back the curtain. Based on the fantastic research material of Dr. Sudheendra S G, we're doing a deep dive into the graphics pipeline that powers literally every game you play.
All right, let's just start with a truth that'll kind of mess with your head. That photorealistic train station you see in a game? It's not real, not even close. It is, and I quote, 2.1 million vertices combined into 3.5 million triangles. What you're really looking at is a staggering collection of mathematical points, all painted with light and color by your GPU. It's an illusion, yeah, but an incredibly sophisticated one.
So that really brings us to the big question for this whole explainer, right? How does a bunch of code become a breathtaking, interactive universe? Well, that's what we're here to find out. We're going to walk through the entire process, step by step.
Okay, so let's get into the fundamental principle behind this grand illusion. I want you to forget the final image for a second. It doesn't matter how complex a character's face looks or how massive his city feels. Everything, and I mean everything, starts as a simple collection of points in digital space.
And this right here, this is the absolute bedrock of 3D graphics. Every single object you create or see is built from just two simple things: vertices, which are basically just coordinates, an x, a y, and a z, and triangles, which are the flat surfaces that connect three of those vertices. Every single model, no matter how detailed, is really just a massive mesh of these simple triangles.
So we've got our objects, and they're made of millions of tiny triangles. The very first major step in what we call the graphics pipeline is something called vertex shading. Its one and only job is to figure out where every single one of those points should end up on your flat 2D monitor.
I mean, just take a look at this locomotive. It looks solid, it looks curved, it's incredibly detailed. But the GPU sees it for what it really is: a collection of almost 400,000 points, all stitched together to create over 750,000 flat triangles. That is the blueprint it has to work with.
Now, to get that blueprint placed correctly, the GPU runs through a series of mathematical steps, or transformations. First, it puts the object into the game world. That's model space to world space. Then, it pivots the entire world so that it's aligned with your point of view, the camera. And finally, it takes that 3D view and squashes it down onto the 2D plane of your screen. This happens for every vertex of every object in every single frame.
And the speed here is just insane. Modern GPUs are parallel computing monsters. They are built for this. We're talking about tens of trillions of calculations every single second. That is what gives you those buttery smooth frame rates we all crave, whether it's 60, 120, or even higher. It's pure computational brute force.
Okay, so the GPU has figured out the 2D blueprint of all our triangles. Now it's time to actually fill them in, to color them. This stage is called rasterization. And all it is really is the process of turning that vector wireframe into an image that's actually made of pixels.
It's a pretty direct translation. You see on the left, you've got the mathematical outline, the vector blueprint. On the right is the result. The GPU figures out exactly which pixels on your screen fall inside that outline and, well, it fills them in. It does this for millions of triangles to build up the final image you see.
But this creates a pretty obvious problem right away. In any scene that's even a little bit complex, you're going to have objects overlapping, you'll have a tree in front of a building, which is in front of a mountain. How in the world does the GPU know which pixels to draw and which ones to just ignore? The solution is actually really simple and kind of elegant. It's called a Z-buffer. Think of it like a depth map. For every single pixel, the GPU stores a number representing how far away the object covering it is from the camera. Then, when another object tries to draw to that same pixel, the GPU just checks the Z-buffer. Is the new object closer? If it is, it gets drawn. If it's farther away, it gets discarded. Problem solved. All right, so we've got the correct shapes in the correct places on the screen, but right now they're just flat, lifeless cutouts. This is where the magic really happens. The final step is called fragment shading, and this is where the GPU simulates light and shadow to give these shapes depth, texture, and a sense of realism. So this is our starting point. After rasterization, we've got the shape right, the base color is there, but it looks like a cheap plastic toy. There's no sense of volume, no material, no life to it at all. To fix this, the GPU has to understand the object's form, and it does this by calculating what's called a surface normal for every point on every triangle.
A surface normal is just a line that points straight out from the surface, telling the GPU which way that little piece of the object is facing. And now, here it comes. The GPU knows the direction of the light source in the game, say the sun, and it knows the direction of every single surface on the object. By simply comparing those two angles, it can apply realistic highlights and shadows. And just like that, it transforms that flat shape into something that feels tangible, something believable.
At its core, the math is actually pretty straightforward. If a surface normal is pointing towards the light, that spot gets brighter. If it's pointing away, it gets darker. It's this simple logic, applied millions and millions of times per second, that creates the convincing illusion of light and shadow in a game world.
Now, everything we've just covered, vertex shading, rasterization, and fragment shading, that's the fundamental pipeline. But of course, modern graphics, well, they push things much, much further. So let's just briefly touch on a few of the cutting-edge techniques being used today.
For example, you've got ray tracing, which goes way beyond approximation by simulating the actual physics of how light rays bounce around a scene. This is how we get those mind-blowing realistic reflections and soft shadows. Then there's AI-powered stuff like DLSS, which is just brilliant. It renders a game at a lower resolution and then uses machine learning to intelligently upscale it to a sharp 4K, giving you this huge performance boost. And all of this is possible because modern GPUs have specialized hardware, RT cores for ray tracing, tensor cores for AI, all running these insane tasks in parallel with the standard rendering pipeline.
So, after all that technical detail, let's just pull back for a second and ask, why does any of this matter? What's the ultimate point of all this insane math and engineering?
It matters because this fundamental pipeline is the unsung hero behind the entire evolution of gaming. The core principles that drew the simple blocks of Super Mario 64 are the same ones that, just massively accelerated and enhanced, now render the photorealistic worlds of today. It really is a testament to the power of getting the foundation right. And that's really the whole point, isn't it? Every single second that you are playing a game, your GPU is running through this entire pipeline, calculating millions of transformations, pixel colors, and lighting interactions, all to create an illusion so perfect, so seamless, that you completely forget you're just looking at math on a grid of pixels. So the next time you're lost in some incredible digital world, just take a moment to remember what's happening behind the curtain. It truly is an orchestra of math, algorithms, and silicon, all performing in perfect harmony at speeds that are almost impossible to comprehend, just to make a world feel alive.
And all this really leads to a final, pretty exciting thought. We've come so far, so incredibly fast. As this technology keeps accelerating, as AI and real-time simulation get even more powerful, what does the future of these digital worlds that we build and that we inhabit truly look like? It's something to think about.